What's the worst possible way to compute decimals of pi? Previously, in the RH Saga, we have seen the Dirichlet L function LA of S many times. This L function is 1 minus 1 over 3 to the s plus 1 over 5 to the s minus 1 over 7 to the s, and so on, in a repeating pattern. Setting s equal to 1 gives 1 minus 1 over 3 plus 1 over 5 minus 1 over 7 plus 1 over 9, and so on. And if we take a lot of terms here, say 5 million terms, we get 0.785398113, and so on. What is this number? Well, multiplied by 4, that gives 3.1415924535, and so on. And you recognize this number, right? How many decimals did we get? Well, this one is wrong. So we did get 7 digits right for the price of 5 million terms. This slow convergence rate makes this one of the worst possible methods for pi. At the same time, there is something amazing about the fact that this L function, just a simple repeating pattern, it somehow knows about the number pi. Today, we will dive into this world of so-called special values of L functions. And our first example is that LA of 1 is exactly pi over 4. The Riemann zeta function, evaluated at 2, is, by definition, 1 plus 1 over 4 plus 1 over 9 plus 1 over 16, and so on, the reciprocal square numbers. This limit is 1.644934, and so on, which is not just some random real number. This is exactly pi squared divided by 6. Similarly, zeta of minus 1 is exactly minus 1 over 12. Both of these are very famous. The first is the Basel problem, and the second is the so-called sum of all natural numbers. These have been covered in many wonderful YouTube videos elsewhere. For the L function of an elliptic curve, we saw last time that L of 1 is either 0 or non-zero, and this difference holds the key to whether the set of rational points is infinite or finite. Or at least this is so if the BSD conjecture is true. Another example. Recall the L function Lk associated to the Gaussian integers. Let's compute Lk of 0. This value is exactly minus 1/4. And this is, in fact, a special case of a very famous theorem in algebraic number theory called the class number formula. The number 1 here is the class number of the Gaussian integers. And when the class number is 1 for some number system, that means that every number has a unique factorization into primes. For example, 5 can be factored into 2 plus I times 2 minus I. These are primes in the Gaussian integers, and there is no other such prime factorization. The 4 here is a counting number, and it counts the invertible elements in the number system. In our case, 1, I, -1, and -I. 2 comments here. First, the word invertible element means an element that can be multiplied by some other number to yield the answer 1. For example, I can be multiplied by -I, and that is 1, and hence I is invertible. Second, when we say there is no other factorization, we mean no other except that we could multiply the primes with a pair of invertible elements. For example, if I multiply this one with I and this one with -I, we get 2i minus 1 times -2i minus 1. In any case, the philosophy of the pi computation, the Riemann zeta values, the BSD conjecture, and the class number formula is that a single L function value, so that's just a shadow of the entire L function, this can still carry some very deep information about the primal object underlying the L function. I want to do one more advanced example. This one also illustrates that the concepts we have been covering in all previous episodes now means that we can talk about some pretty high-level stuff. The example I have in mind was covered in that survey of Brian Conrey from episode 1 on page 54. We take the elliptic curve defined by y squared plus xy equals x cubed minus x squared minus 2x minus 1. This is 49.A4 in the LMFDB. It has an L function, of course. We can take the symmetric kth power of this L function. That operation gives us a new L function of higher degree. Let's focus on when k is an odd number, so we can write 2n minus 1. This elliptic curve has a very special property called complex multiplication, which implies that the symmetric power L function can be decomposed as a direct sum. Let's just say L1 plus L2 plus L3 all the way up to Ln. Each of these L functions has degree 2, so the total degree is 2n. Any of these L functions has, of course, a central value at the symmetry point. Central values in general are very mysterious, but the miracle here is that there is a formula for that value, which was found by some of the most legendary L function researchers in history, Gross, Zagier, and Rodriguez-Villegas. The formula says that the central value of Ln equals 2 times 2 pi over square root of 7 to the power n times a certain number omega to the power 2n minus 1 times a certain number a depending on n. All of that divided by n minus 1 factorial. So, what's omega? Well, omega is gamma of 1 over 7 times gamma of 2 over 7 times gamma of 4 over 7, divided by 4 pi squared. There is a separate recursion formula for these numbers a of n. I think it's the craziest recursion I have seen in my entire life. You can check Conrey for the details. So, all of this looks complicated for sure, but if you look at each factor, it is something that you can compute. But what kinds of numbers are they? Well, 2 and a of n and n minus 1 factorial, these are rational numbers, so very easy in some sense. 2 pi and square root of 7 and this omega, they are periods. The numbers we encountered in that very first article of Riemann. So, check out Conrey again if you want more details on this example. The general pattern that I wanted to convey is that values of L functions can, in great generality, be expressed as rational numbers times some period numbers. All of this brings us to the question that was left unanswered back in episode 1. What is a period? Definition. A period is any number of this form. Here, P is a polynomial and R is a rational expression, so polynomial divided by polynomial. And these are required to have coefficients in Q, so rational number coefficients. I will make up an example with 2 variables, say x and y. Let's take R to be x plus y divided by x squared minus 5. And then integrate that function over this region. That's a domain bounded by an ellipse, and this integral, this number, whatever it is a period. It's 2 variables, so I should spell out that this is a double integral with respect to dx and dy. A more complicated example. I take R to be 1 over 1 minus xyz. I take the triple integral over the unit cube. That means x goes from 0 to 1, and the same for y and z. Now, very surprisingly, this integral is equal to Riemann zeta of 3. Another example. The integral of 1 over x from 1 to 2 by elementary calculus, that is log of 2. So this number, log of 2, is also a period. The number pi is a period because it is the area of the unit circle, and that's also an integral. So, which numbers are not periods? Well, it's very hard to prove that a specific number is not a period, but conjecturally, the number e and also the Euler-Mascheroni constant gamma should be not periods. If I write down this rational expression and integrate over y from 0 to 1 and then x from 0 to infinity, this would be a period if the integral converged. Here, if I throw in a factor e to the minus x, that's no longer a rational expression. But this integral now is equal to the Euler-Mascheroni constant. Here, it's a rational expression times e to some other rational expression, and these more general numbers are called exponential periods. Let's do all values of Riemann zeta at integers. First, even positive integers. At 2, the value is pi squared over 6. At 4, it's pi to the 4 over 90. At 6, it's pi to the 6 over 945, and so on. Always a rational number times the obvious power of pi. At 3, an odd number, we had the integral formula with 1 over 1 minus xyz. There is also the Ramanujan formula, which is this rational number times pi cubed. Looks like the other ones, but you also have to take minus 2 times this infinite sum. Here you see pi cubed and k cubed. That's related to the s value 3. And you also have this e to the 2 pi that you may have encountered elsewhere. There are similar formulas for zeta of 5, zeta of 7, and so on, worked out by Plouffe, Chamberlain, and Lopato. At negative even integers, we have seen before that the values are 0. For these odd integers, we get certain rational numbers. Minus 1 over 12, 1 over 120, minus 1 over 252, and so on. These are a bit mysterious. At minus 11, you have this number, and then it's minus 1 over 12 again. Here, there is a wonderful general formula. Zeta of minus n is minus 1 to the n times bn plus 1 over n plus 1. Here, this bn plus 1 is a Bernoulli number, and you can look up the definition. Zeta of 0 is minus 1/2. Zeta of 1 is infinity, or rather, the zeta function has a pole at s equals 1. However, if you subtract the term 1 over s minus 1 from the zeta function, that pole is cancelled. And the value at s equals 1 of this modified function is gamma, the Euler-Mascheroni constant. The symmetry point at s equals 1/2 is not an integer. So that's not usually called a special value. The value is close to minus 1.46. I don't think it's a period. That would be very surprising. Maybe, though, it could be an exponential period. I don't think anyone knows. Could be something to investigate. Sometimes we also look at the derivatives of an L function. For example, the first derivative of zeta at 0 is minus 1/2 times log of 2 pi. Looking at derivatives is also what you must do to formulate the BSD conjecture in its most precise form, the so-called strong version of BSD. A few remarks. First, we can think of any special value as an invariant of L functions. Like the value at 2 is a number that you can compute from any L function. If we instead take log of the special value, we get an invariant that is additive. So for any m, log of L of m is an additive invariant, so it's an element of L star. At least this works when the value is positive, so that log is well defined. Second, there are many theorems and many deep conjectures about special values, and all of these could potentially hold some clues for us for F1 geometry. So a few key ideas would be Bernoulli polynomials for special values of Dirichlet L functions, the BSD conjecture, of course, for elliptic curve L functions at the central point. There is Zager's conjecture for Dedekind zeta functions of number fields. Then there are various formulations of frameworks that sort of covers all L functions, or at least some very general class. I want to highlight the Bailinson conjectures, the ETNC or equivariant Tamagawa number conjecture, and also a more recent framework proposed by Flach and Morin. Finally, if you really wanted to compute pi, you could use the L value we started with. There are tricks for accelerating the rate of convergence there. However, a far more efficient method is Chudnovsky's formula. And I just want to share with you this beautiful paper of Lawrence Miller, available in arXiv. Here you find the formula and all of the theory behind the proof. It involves modular forms, and in particular this mysterious theory called complex multiplication. Next time, we will return to more of what we talked about in episode 1. That will be the mind-blowing connection between special values of L functions and quantum field.